Hi, my name is Philip, and today we'll talk about the Faraday's law and how it is used to generate electricity from movement, and we'll show it on an example so you can properly understand it later in the video. So this is the basic notation of the Faraday's law, and it says that the change in magnetic flux through a loop gets us the induced current. And what do I mean by that? So let's imagine we have a loop of wire and it's moving. And at the start, when it starts moving, uh, the the magnetic field or the flux of the flux through loop, the flux of the magnetic field is lower than at the end of the journey or of the when the loop stops moving. So while it's traveling through a magnetic field, the magnetic field gets stronger and stronger. And while it's moving, only while it's moving, not while standing, but while it's moving, there will be a current in the wire, and that's what we'll try to calculate in the example. But before we get to the example, we'll have to talk about Lenz's law. And Lenz's law tells us the direction of the current that the loop will have. So it will be counterclockwise or clockwise. So let's say we have a counterclockwise direction of the current, and every current has its own magnetic field generated by the current, right? That's what we talked about in the last video. And so what will be the magnetic field here? So as we talked in the previous video, we point our thumb in the direction of the current, so now it's pointing upwards, and we wrap around the wire, so the magnetic field will look like this. And what will be the magnetic field inside the loop? Well, it will be in the same direction as the magnetic field that we have in the loop. So it will be more magnetic field there than it was before. And if we have a change in the magnetic field, we will have a current. And if we have a current, we will have a stronger magnetic field, and this will continue to the infinity. And that would then we would have like the infinite source of energy, and that's not what's happening, right? We would violate the law of the law of conservation of energy. So that's not what's happening here. Instead, we will have the current pointing in the clockwise direction, or we will have the current in clockwise direction. And now the magnetic field points in difference, or in the opposite direction. So this is correct, and so we will have to remember that every time we're calculating with this, or in the example, we will have to remember that the magnetic field generated by the current will have to be the opposite direction to the magnetic field that we have in the loop. Okay, so we have a magnetic field that's pointing into the screen, and we have a loop of wire, and the magnetic field is getting stronger and stronger to the left. So our loop of wire, or our wire, will be moving to the left. And now what will be the direction of the current? So we know the magnetic field produced by the current will have to be in the opposite direction of the magnetic field that we have in the loop. So let's say we have a direction of the current that's pointing up now, so in the counterclockwise direction. So the final magnetic field in the loop produced by the current will be in the opposite direction of the to the magnetic field that we have here. So that's the correct answer. So the current, or the direction of the current, will be in the counterclockwise direction, and the current will be there only while it's moving and while the magnetic flux. What's the magnetic flux? The magnetic flux is the amount of the, let's say, the amount of the magnetic field that's in the loop. And while it's getting to the left, or while it's traveling to the left, the magnetic field is getting stronger and stronger. So the magnetic flux is changing, right? The Faraday's law is the change in the magnetic flux gets us the induced current. So we have this animation. While it is moving to the left, we will have the current in the counterclockwise direction. And it would work the same if the loop wire would start in the stronger magnetic field and would travel to the right, to the less denser magnetic field, and the current will be in the same direction, but we would go from the stronger magnetic field to the lesser or less denser magnetic field, but it will work the same. The direction will be the same. Okay, so let's show this on an example with some actual numbers. So we have this magnetic field that's at the right. We have a weaker magnetic field with only 5 teslas, but as we move along to the left side, we have the magnetic field with 10 teslas. We have the wire with some resistor, and what we want to know is the current, or the amount of the current that will be in the loop while it's moving to the left. And we will use this. Yeah, we have this animation here, and we will use this equation. And what this equation tells us is that to get the voltage generated by the magnetic field, we'll need to know the n there. That's only the number of loops or the number of wires, and so we have only one wire here, or only one loop. So that we will ignore that. Because it's only like one, so we can just ignore that. Then we have this omega of the magnetic field, and that's the flux, that's the amount of the magnetic field in the loop. And to calculate this flux, or this delta flux, is a difference between the flux at the start and the difference between the flux at the start and the flux at the end. And to calculate the flux at the one time, at the start and at the end. So this is the equation for calculating the magnetic flux at the one time. And we will need to make this twice, once at the start with the 5 teslas, and once at the end with the 10 teslas, and then we will make the delta of the difference between these two, and then we can put it into equation for the voltage. So let's do it. So here are the equations. So the B1, or the omega, the flux B1, is at the start, and we have 5 teslas and 4 meters squared, and the cosine there is that's the cosine of 0 degrees, because they're perpendicular to each other, and the cosine, or the alpha, is the or how much is the loop diverged, or how much is the loop in different angle than they are perpendicular, right? We will show. We will have in the next example. We'll show this more properly. Just ignore it. This is the cosine of 0 degrees, and that's 1, so we can ignore it. Okay, so we have this B1, B2. One is to the B1 at the start. We have a lower magnetic flux, so that's only 20 Tesla meters squared. But when we end our journey, or when the loop stops moving, we have the magnetic flux of 40 Tesla meters squared. So we just make the difference there, and that's the difference is 20 Tesla meters squared. And now we can put it into equation. So we have just 20 divided by time. I forget to mention at the start, what's it called? The loop is moving 5 seconds. So while it's moving, so that's the delta t, right? I hope you understand. It's moving 5 seconds to the left. So we just put in the seconds there, and we have voltage of, or while the loop is moving, we have a voltage there of 4 volts. And now we can just use the Ohm's law, and that is that the current is equal to voltage divided by resistance. And we have the resistance there, so we can just put it in, and we have 4 volts divided by 2 ohms, and the final current that we will have in the loop while it's moving is 2 amperes. So now we will show this, or this is like the basic idea behind the Faraday's law. But now we will show how it's used to actually how it's used in the power stations, and how we can get from movement, or from how we can get from movement electricity. Okay, so here is an example where we have the loop that is rotating instead of only moving from right to left. So we have some area of 4 meters squared, then we have some magnetic field of 5 teslas, then we have some resistance, time, and that's actually important, time that the wire will rotate 45 degrees. So in 0.25 seconds, the wire will rotate 45 degrees, as you can see. And we will want to know what current, or the amount of current that will be in the wire while it's moving this distance. And again, we will use the same equations as in the previous example. Again, we have 2 cases. We have the case where the wire is flat, as again the first, like when it starts moving, and then we have the case with the 45 degree. So again, we will calculate the fluxes of both of the cases here. The first case is when the magnetic field is perpendicular to the wire, and then we have the case with the 45 degrees. So the first one will again just multiply the magnetic field and the area, and we'll get 20 Tesla meters per 20 Tesla meters squared. And in the second case, we will use the cosine of the 40 of these 45 degrees, and when we multiply all this together, we'll get this neat number, 14.14 Tesla meters squared. And now we can get the difference, and we can put it in to our equation. And with the use of the Ohm's law again, we get that the current will be 11.72 amperes. So where is this actually useful? Well, as I said many times before in this video, it's used to generate electricity. It's used to in all the most of the power stations, like there is water electricity, there is wind electricity, and basically what all this does is it takes some movement on something, and it turns it into current. So and this current is our electricity. Well, in the end, so that's all from me today, and see you in the next video, then where we will talk about how electric motors, how these Teslas are using electricity. That's the reverse, right? We will use electricity to make some movement, and we will show again an example how it works. So see you there.